Quiero dar la bienvenida a nuestro conferenciante especial del día de hoy, el ingeniero y profesor, dice que no le digamos así, John McDonald. El ingeniero McDonald es director y también es estratega, técnico y desarrollador de políticas para General Electric en el área de energía y energía digital. Tiene 38 años de experiencia en este ramo de la industria. John obtuvo sus grados de licenciatura y maestría en Ingeniería Eléctrica en la Universidad de Purdue y una maestría en Administración de Negocios con especialidad en Finanzas en la Universidad de California en la ciudad de Berkeley. Es miembro honorario de Eta Kappa Nu y Tau Beta Pi, miembro del IEEE y fue galardonado con la medalla Milenio del IEEE en el año 2000. John fue presidente de la IEEE PS, presidente del Consejo de la Smart Grid Consumer Collaborative, miembro fundador del programa de embajadores de marca del IEEE y vicepresidente de actividades técnicas para la Comisión Nacional de Estados Unidos del SIGRE. Fue director del IEEE División 7 de 2008 a 2009 y es miembro del Comité Asesor para la Conferencia Anual Distributec. Es instructor de un curso sobre redes inteligentes en el Instituto de Tecnología de Georgia y de otro para la propia empresa General Electric. John ha publicado 40 trabajos y artículos en las áreas de SCADA, SCADA EMS, SCADA DMS y comunicaciones, y está registrado como ingeniero eléctrico profesional en los estados de California, Pensilvania y Georgia. Es autor del libro Automating a Distribution Cooperative from A to Z, automatizando una cooperativa de distribución de la A a la Z. Es editor en jefe y autor del capítulo sobre automatización e integración para el libro Electric Power Substation Engineering y muchas otras obras adicionales. Además, me da mucho gusto constatar que es conocedor de nuestro instituto, ha estado aquí con nosotros en otras ocasiones, conoce bien este ambiente, nos conoce a algunos y para animarlo a que nos dé una charla, como siempre nos la ha dado de manera extraordinaria, yo les quiero rogar que lo recibamos con un aplauso. Muchas gracias.
Good morning. I could give Spanish, but habla español poquito, very little. So I will give the talk in English. I've been to Cuernavaca a number of times. Been in this building a number of times with both with the Institute as well as with the IEEE Morelos section, okay? That is one of my favorite, in all my years of IEEE, one of my favorite sections here, very active, very strong leadership, and many activities that I've participated in a number of times with tutorials and talks, and always enjoy trips here to Cuernavaca. So what I'm going to talk about is looking beyond smart grid. Okay, what's the future of energy? Not just smart grid, but beyond smart grid. In other words, a vision for the future. And I have a number of different perspectives as a result of my leadership at IEEE Power and Energy Society, and also leadership on the IEEE Standards Association. For over 30 years I've been leading standards work, and also the IEEE Smart Grid Steering Committee. We're putting strategy together for IEEE, all of IEEE, not just Power and Energy Society, but all of IEEE with Smart Grid. And then CGRE, the U.S. National Committee, I'm in charge of all the technical activities for the United States. So that's another opportunity to see technology more from a global perspective with SEGRE. And also, it's not just technical people, but also executives of companies. Okay? So, what we're going to talk about is, the very first thing is, what's happening in the world around us, right? With the jobs that we have, we make decisions every day for our work. How do we know that those decisions are the best decisions for the company that we work for? Okay? Another way to look at this is, how often do we get outside of our company in industry, talk with other people in industry, and really understand what's happening in the world around us? If we stay at our companies every day and we don't go outside, okay, we're very internally focused. We know what our company's doing, we may not really know what's happening in the industry, right, around us, which means that decisions we're making for our company may not be the best decisions when we take into account the trends, right? The trends in the industry. So let's start with what some key industry trends are. What's happening in the world around us? Second thing, which is very important to Mexico and very important in many places in the world, is the integration of renewables. Okay? And third is the concept of a solution, and what we say holistic solution. And this is really new with smart grid the last 6 or 7 years, okay? Then managing the data, big data, new software analytics, and the concept of enterprise data management. Then we got to spend some time on industry standards, because we won't be successful unless we implement the correct standards, okay? And then what's happening in Mexico now, and what needs to happen in many places in the world, is looking at new policy, new regulatory models, okay? Like in the United States, we're using regulatory models which are very old, and they don't incentivize the utility to make the investment in the right ways that benefit the customer. Okay? So what's a new regulatory policy? And then I'll finish up with some experiences I had with my very first job out of graduate school at Purdue. I worked for 5 years in downtown San Francisco with Bechtel Corporation, and some of the things I learned with that first job. Okay? So let's look at the... So, first one is, we're transitioning from what we say devices and systems to what we call holistic solutions, okay? A device would be like a microprocessor-based device. In the late 1980s, when we were updating the standard on SCADA, Supervisory Control and Data Acquisition, there's an IEEE standard C37.1, which is how to define and specify SCADA systems. We were updating that in the late 1980s, and we needed a new term to use for all the new microprocessor-based devices that the manufacturers were selling in the industry. We had many, many new microprocessor-based devices, and there's two parts to the definition of this new term that we came up with then, called Intelligent Electronic Device, or IED. First part is that it has internal processing capability, but the second part is that it has two-way communications, right? And that's very important, because the older electromechanical devices did not have communications. You know, they were standalone. So if we wanted to read electromechanical device, we went to the substation, right, and read it. Now we have a new, at the time we had a new family of devices with two-way communication. So each of these devices could be a node in a network, right? Not just a device, but now a node in a network. And then systems. You know, we have many traditional systems, an energy management system to control generation transmission, distribution management for the distribution system, outage management, right, geographic information system, traditional systems. But we've had these for a number of years. Now with the beginning of smart grid 6 or 7 years ago, we're thinking differently. We're thinking of an integrated solution, right? The difference with an integrated solution is we don't develop it like we do a traditional product, but we start with the customer, the electric utility, and we spend a lot of time with the customer and say, what are your business needs? You know, what are the things that you're trying to accomplish this year? You know, talk to the CEO. What are your 3 objectives for this year, right? Or talk to the executive vice president. What are the things that you want to accomplish? And we gather that information. And then the question is, what technology components do I have, or that I can develop, or I can partner with another company? And I integrate these technology components together, and that's my integrated solution that addresses the business needs of the customer, okay? And we went through this process about 6, 7 years ago, and there were 6 integrated solutions that had the strongest business cases for electric utilities. I'll show you what those are, okay? And I'll show you the examples of these 6, the technology roadmap for these 6 solutions. So this gives us an opportunity because the device and the system have a business value to the customer, right? A microprocessor-based device, like a protective relay, has value. A system has value. But what's important is the greater value, the stronger business case is the integrated solution, okay? So many universities now, for instance at Georgia Tech in Atlanta, where I live, there's a curriculum called system engineering. And that curriculum teaches students, think about the big picture. Don't just be happy with the device. That device has 2-way communications. The greater value proposition, right, to the customer is not just that device, but it's the integrated solution. Always think of the big picture, okay? That's very important. And that's what the systems engineering curriculum does, is it emphasizes always be thinking of the big picture. How can I put building blocks, technology components together? Okay? So that's an important trend. And it's holistic because we're not just talking about satisfying the needs of one group in the organization, not just planning, power quality, or asset management, but we want to satisfy the needs of the entire organization, holistic, okay? What we do today should not just be for one group, but we should think about the whole organization, right? For instance, when the metering group is thinking of buying 2-way communications for smart meters, don't just think about the requirements for the smart meters, but think about that communications infrastructure for smart metering is 2-way, and it's around the whole service area where all the meters are located. That communications infrastructure could also support distribution automation. So the metering group should get together with the distribution group and say, let's make one investment for the whole organization in communications. And that communications infrastructure can support multiple groups. Not just one, but multiple groups. If we think of the big picture, think of the whole organization, the business case is stronger because one investment now meets the needs of more than one group, right? So the benefits to the organization are greater. How do we define success? It's not just technology. Okay? Technology is important, but it's also standards. Why? Because I'm going to show you examples of these integrated solutions. How can we get a number of technology components from different vendors all communicating with each other successfully and exchanging information successfully? The key term here is interoperability, right? We want successful interoperability. Standards is key, okay, and I'll show you that. And then the last part is policy. Policy is the strongest driver for investment in technology, right? Policy is the strongest driver. No question about it. So it's policy that incentivizes customers to buy renewables, for instance, rooftop solar PV to install on their roof of their home. Why are some countries in Europe have so much wind generation, like Germany and Spain and Denmark? Because in the 1990s, early 1990s, those countries changed policy to incentivize investment in wind, okay? And it's directly proportional. Where policy is changed, the investment is great, okay? Third is flexibility of the grid, and particularly self-healing. That's become more and more important because in the last 5 or 6 years, we've had more extreme weather events than any time in the history of the United States and many countries around the world. We can plot on a graph the number of extreme weather events in the last 5 years, and it's a positive slope, and we're having more and more extreme weather events as time goes on. And so what happens? That puts stress on the grid, right? So we need to think about how can we make the grid flexible? How can it be self-healing? And how can we add reconfigurability, right? And there's two important changes here that we need to make, more from a cultural point of view. One is we need to do more to distribute the intelligence downstream in the architecture, right? The model that we've used for many years is a centralized model. All the information from the field goes upstream to the control center. All the logic's in the control center. The analysis of the data happens in the control center. Decisions are made, and then control commands are sent down to the field equipment. It's a very much of a centralized model. Okay? What we're doing now is we're distributing intelligence downstream. We can run a number of applications at the substation level, right? And these applications then analyze the data at the substation level, make decisions, execute those decisions, and report after the fact, upstream. Okay? It puts a lot less burden on the control center and distributes the intelligence. So the ultimate architecture today is not centralized, but we say it's a hybrid architecture that's a combination of centralized and distributed. The second part of self-healing, once we distribute the logic, is to close the loop on the logic, right? Especially on the distribution system. Once we've tested the logic, take the human out of the loop and close the loop on the logic. Okay? It's very difficult to improve the performance, the reliability of the distribution system if you keep humans in the loop. Because when you look at calculating performance reliability indices like SAIDI, SAIFI, SAIDI, the duration of outages, SAIFI is the frequency of outages. Humans in the loop extend the amount of time it takes to make decisions and carry those out. Once you've tested the logic, we close the loop on a logic, and we can detect a fault, isolate the fault, detect it, locate it, isolate it, and restore service within a minute or two. And in the United States, that threshold is 5 minutes. If we can bring customers back online in less than 5 minutes, it doesn't count against us with respect to reliability. In Canada, that threshold is 1 minute, okay? But in the United States, it's 5, right? So self-healing is important. What happens then if we can do that, distribute the intelligence and have self-healing, we have a grid that's more resilient, okay? Resiliency is a key word today. What we do is when we make decisions based on reliability and redundancy. Buy equipment that's more reliable, let's say, or an architecture that has automatic failover, right? Full redundancy with automatic failover for reliability. We can do the best job we can, then an extreme weather event occurs that puts stress on the grid. And then the question is, when the grid is stressed, how well does it withstand that stress? In other words, how resilient was it? So after these extreme weather events in the United States, like Hurricane Sandy, you know, the media then, I did media interviews, and the media would say something like, how come the customers at this utility were only without electricity for 2 days, and the customers nearby at this utility were out of electricity for 5 days? You know, what's the difference? Why is one grid more resilient than the other? And I'll show you in a little bit. It's not just the investment in the technology, but it's the integration of the components, like we talked about, the solution that's important. Then we're putting more and more sensors on the grid. How do we manage the data? How do we use the cloud? We're using the cloud more now with cybersecurity for what we call a hosted model of functions. So if there's smaller utilities that can't afford a purchase of a complete automation system, we can host the functions, and then they just pay a monthly service fee, but they have all the functionality as if they bought a complete system themselves. And we can use the cloud for that. And then social media. So we were just talking a little bit ago. I've got involved in Facebook through my daughter, and I got involved with Twitter through my son. Okay, and it was the best thing I did. And I've always been involved with LinkedIn and how important LinkedIn is for work, right? For work, because all the job changes I've had, and I've been working 41 years full time now in the area of smart grid, but all the job changes were through friends of mine in the industry, okay? And we're connected all through LinkedIn, okay? And LinkedIn, I can't say enough about how important it is to not only have a profile on LinkedIn, but have as detailed a profile as you can and keep it up to date, okay? But I found through Facebook and Twitter how important social media is. I wrote an article, it's been 2.5 years now since I wrote this article. The title of the article was, How Can We Use Social Media to Accelerate the Restoration of Electricity After an Outage? Okay? And it was a cover story of Power Grid International magazine, December 2.5 years ago. And so I want to talk more about social media, because we can use Twitter, the electric utility can use Twitter, empower the customers to say, if you have outage information, like electricity just went out at your house, send us a tweet, you know, with the outage information. And in your customer record at the utility, instead of putting your phone number, your home phone number, we'll put your Twitter hashtag. Okay, so you don't have to be at home when you send us a tweet. You can be anywhere. Once we receive it, we know who it is and what your home address is through your Twitter hashtag. Okay, we surveyed we did a survey last year of thousands of adults, over 18 years old, and we said, what's your preferred way to communicate with your electric utility? And 70% said through social media. 70%. And we need to take advantage of this, you know. We need to do more with social media. There's a lot of advantages to it. I want to talk more about that. And then lastly is we have a disconnect in many utility architectures today between operations and IT, or the information technology, where we need the convergence. We need to bring together the IT side of the utility and the operation side. And what we have is a disconnect when we try to take valuable information from the operation side in devices and systems across firewalls onto the corporate side or the IT side. If these two groups don't work closely together, there's a disconnect in that enterprise, and it prevents us from bringing information over. And what happens is, bottom line today is when a utility spends thousands of dollars for a microprocessor-based device and installs it on the operations side, on average, that utility is realizing only about 20 to 30% of the potential benefits of that investment. There's 70% of untapped benefits. It's like if you spend $5,000 of your own money to buy something, you bring it home, but you're only using it to the extent of realizing about $1,000 of benefits. That's not a good business situation. You want to get 100% of the benefits of your investment. And so I'll show you, there's a number of things that we need to do a better job with enterprise data management. Okay, so there's a number of things going on. The decisions we make need to take all of this into account. So let's look at renewables. We can integrate renewables at the transmission level, right, the distribution level, or at the end user level, right, the three different levels. What are the challenges, though, that renewables gives us, right? Operational challenges with intermittency, but also on the distribution system. We designed the distribution system for electricity flowing in one direction, right? From source to load. And many distribution systems are radial in topology, right? So the feeder brings electricity to the customers, and when we reach the last customer, the feeder ends. There's no loop, there's no tie point to another feeder. It's a radial, so it's a very simple architecture, one wave flow and radial. What happens with renewables? When we integrate renewables on the distribution system, now we have electricity flowing in two directions, right? Source to load, and we have a contribution now from the renewable upstream. So we have two-way flow. What happens with protection? Right? Protection, we have to look at protection. What happens with safety? If I go out to work on a line, I used to be able to just open an upstream device and the line would be de-energized. That's not the case now with renewables. So what are some of the challenges that renewables gives us? Well, one is open circuit overvoltage due to unintentional islanding. Protection ratings may not match fault currents because our rating was based on the contribution from the source only. Now we have a load side contribution. The fault currents vary. As the wind changes or the sun changes, the contribution from the renewable to a fault will vary. So we have varying fault currents due to the distributed generation. And stress on voltage regulation equipment. I want to talk more about that with a specific case study in California. Okay, so these are some of the challenges of renewables. One of the things that we're doing, spending more time on, is the concept of a microgrid, right? And this is an installation that we did probably 5-6 years ago. Very, very good application, a rural area, northern British Columbia in Canada. It's a village that has, no tie to an electric utility, but this village had fuel cells, has solar generation, has hydro generation, and the traditional generation is diesel, right? So in a rural area like a village, it's very expensive to bring the diesel fuel to the village. Also, when the diesel generators operate, what happens? They send carbon dioxide to the atmosphere, right? So there's pollution to the atmosphere. So I say, okay, so we have these generation resources. We have residential load and industrial load. So the microgrid controller in the upper left corner there, its objective is every couple seconds, take a look at the load requirements, right? But also maximize the resources, minimize the diesel generation, and maximize the generation from the renewables, right? And so this has been operating very successfully. Maximize the use of the renewables, which reduces the millions of tons of carbon dioxide which go to the atmosphere, okay? So microgrids are also very good application on military bases and university campuses. Most universities now have implemented or are implementing microgrids to do a better job of using energy efficiently around the campus. Okay? Here's some solutions. How do we bridge the intermittency of renewables? You know, we call frequency smoothing. Turns out that we have a very fast start thermal generator that runs on natural gas, right? So the price of natural gas, went down substantially. And so the question was, how could we use the lower cost fuel but still have the speed of response to keep up with the intermittency of wind and solar? This is a fast start, fast acting thermal generation that can do that. And also, of course, we could use energy storage, right, to bridge the intermittency, okay? Now, another aspect of this is with renewables is high penetration of renewables can bring a lot of volatility to the grid, right? Because if we have high penetration, that means it's going to have more impact on the voltage and the reactive power, right? And we're going to introduce volatility, and if it's rooftop solar panels on your home, that volatility is going to be on the low voltage network, right? So how can we compensate for that at the point where the volatility is introduced? So there's a new family of power electronic devices we call low voltage network dynamic grid edge controller. It's installed on the low voltage network, dynamic because it continuously compensates for voltage and reactive power, and it's installed at the edge of the grid, possibly on the customer near the end of the feeder. Okay, we'll talk more about that. So here's what I want to talk about here is I was looking at the impact particularly of high penetration of rooftop solar PV on the distribution system. And wrote an article for Power Electronics magazine and worked with San Diego Gas and Electric and Arizona Public Service. These two utilities have experienced more of the impact of high penetration than any other utility in the United States, okay? So working with them, and actually got voltage waveforms from a feeder in San Diego. And this feeder, think of one distribution feeder, and it's actually along the ocean, the Pacific Ocean, where the homes are right on the ocean. And think of one feeder, over 35% of the homes on one feeder all have rooftop solar panels. That's very high penetration, okay? In the morning, there's what they call a marine layer of fog from the ocean that completely blocks the sun from seeing the homes, okay? But as the morning goes on, that fog burns off, and all of a sudden, all of those homes go from 0% sun to 100% sun instantaneously. Okay? What happens to the voltage on that feeder when you have over 35%? The voltage spikes, and then as the clouds go in and out, it oscillates. The voltage oscillates, okay, over a pretty wide band. At the beginning of this article, I have the voltage waveforms, the actual voltage waveforms from this feeder, and you can see the volatility, okay? So what's the impact of that? And what does that mean for the grid of the future and how we monitor and control, particularly control the grid of the future? Well, let's take a look. And this particular feeder, in the substation that feeds that feeder, there's a tap changer, an online tap changer. We know a tap changer is mechanical, has 32 discrete positions, and the objective of the tap changer is as the primary voltage changes, the tap changer changes tap positions to keep the secondary voltage constant, right? Because at a customer, you want the voltage to be constant at the customer's premise, home, business, whatever. Normally on this feeder with no PV, tap changer was operating 5 times per day. Lifetime designed to be 30, 40 years, okay, for a tap changer. Now with 35% penetration of rooftop solar PV on that feeder, the tap changer is operating 90 to 100 times per day instead of 5, and its lifetime now is well less than 5 years. Okay, so the takeaway is mechanical means of control for the grid of the future with high impact of renewables. Mechanical means of control just aren't feasible. They don't make sense. So we have, and our competitors have now, a power electronics-based tap changer. Okay? So this article I wrote about was new applications of power electronics as we look to the future. Okay? Second is the low voltage network dynamic grid edge controller, what we talked about before. New application of power electronics, new family of devices. And there's a number of these installed in different pilot projects in Mexico from a company called Verentech in San Jose, California. Okay, as well as a number of utilities in the United States. All right? So it makes sense that let's compensate for the volatility on the grid at the point in the grid where the volatility is introduced, which is the low voltage network here. Okay, so new applications of power electronics. Third is we need more capability from inverters, and we call this smart inverter. Okay, and we have a list of new functionality that we'd like to see from inverters, and also additional capability to externally control the inverter. The inverter is a very good source of reactive power compensation. It's a very good VAR resource. Okay, and we amended the IEEE standard 1547, which is the standard on the rules to integrate renewables to the grid. We amended that a year ago so that we can use inverters now for VAR compensation. Okay, so this is a smart inverter. So these are 3 new applications of power electronics. So the bottom line here is, when I go to universities, I still see the power electronics researchers in electrical engineering still doing work separate from the power system analysis group, the researchers. And we need to combine these two. We have new applications of power electronics in power system monitoring and control for the grid of the future. We need to combine this expertise now and work together. Okay, because this is just 3 of many new applications of power electronics. So if we sum this up, the lessons learned is, what are some challenges here with integration of renewables? Lack of transmission. You know, a good example of this is the state of California that passed new policy that said the 3 investor-owned utilities in California by 2020, 33% of their generation must be from renewables. So policy was passed. My problem with that is there was no operational analysis done before policy was passed to say, what kind of an infrastructure will I need in the future, transmission infrastructure, to support that much addition of renewables? After the policy was passed, the analysis was done, and it said 10 new transmission lines were needed in the state of California to handle that much more renewable generation, to couple, to be able to couple it to the grid. And as you can imagine, one new transmission line in the state of California is virtually impossible, let alone 10, okay? So one of my real pet peeve, one of my points that I always say is policymakers shouldn't be allowed to set policy unless an operational analysis is done first, and the policymakers and the engineers, the analysts, all need to work together. Don't pass policy unless it's possible to do it, right? There's an infrastructure in place to support it. Lack of control area cooperation. So this is rules so that the regional groups work together. Our market rules and market contracts need to support renewables. Unobservable distributed generation is behind the fence. There's no monitoring, right? We don't know what's happening. And I'll tell you, a good example of this is in the United States today. I don't know what the situation is in Mexico. In the United States, we have 48,000 distribution substations in the United States. Only about half of those today have any kind of automation installed. Okay? Only about half. So we have what we say large areas of unobservability. We don't know what's happening in those substations. There's no automation. But what's worse yet, for someone like me who works in automation, is of the half of the substations where automation is installed, remember now this automation has two-way communications capability. Only half of the installed automation is using the two-way communications capability. The other half is operating standalone, like we used to do with electromechanical devices. We're paying for new technology, and we're not using it. We're not taking advantage of the capabilities of the technology that we're buying. We're putting it in, operating it like we used to with older devices. Okay? And then looking at light load and high risk periods with operational strategies, thinking of new ways to do things. But enablers are being able to do some forecasting. Having a thermal fleet now with units where we can have quick starts, deeper turn down, and faster ramps, like we talked about, faster operating thermal generation. More spatial diversity, so the distributed generators is not all on the same feeder, but it's distributed spatially around the grid, which helps us with the operational challenges of renewables. And then renewable plus distributed generation plus demand response and grid-friendly renewables. So we have challenges, but we also have enablers too. Okay? And I think what's the bottom line here, what's important is before we do anything with renewables, we need to study. We need to do power system analysis studies. And this is just some examples of studies that our energy consulting group at GE has done for a lot of different organizations and customers on wind, okay? And the point here is that, the Chinese, when we asked the Chinese what their plans for smart grid were, they said before we think about smart grid, we need to have a strong grid. Right? Very important. We need to make sure our infrastructure is sound, our communications infrastructure, our IT infrastructure. If we layer new intelligence on top of a weak foundation, it's not going to be successful, right? So let's look at the foundation first. Let's do the proper system studies first and analyses and see what do we need to do with communications, what do we need to do with IT, what do we need to do, like we said, with our transmission or distribution infrastructure to be able to support the renewables that we want to add to the grid, right? And have a stable economic system, okay? So let's look at holistic solutions. I want to start with something. Instead of smart grid, I like to say smarter grid. Smarter. Because you know why? I've been working 41 years now in the field of power system automation. I've been adding intelligence to the grid all my career. This smart grid is not new. Many of us in this room, we've been doing this work for a long time. So this isn't just new. We've been doing it for a long time. So let's look at the difference between what we've been doing in gray and the new things that we're doing in the last 5 or 6 years with smart grid. In other words, let's acknowledge the fact that we've been adding intelligence to the grid for a long time. And then let's say, okay, what is it that we're doing new? So, shaded in gray here is what we've been doing. Okay? And even some of that is changing. I'll show you. But in light green here is the new things that we're doing. I love this slide. I could spend days just going over each of these and what we've done in the past and what we're doing now. But you know, we're doing voltage control now, which has a stronger business case. Instead of doing voltage control by itself, we're integrating it with VAR control, reactive power control, integrated volt-VAR control. As we know, voltage is directly proportional to load. So when I control voltage, I manage load, right? So we've been using voltage control to manage load so utility doesn't exceed a previous peak load condition. We can do voltage control. But we also know that reactive power, VARs, is directly proportional to losses, right? How we reduce the losses on the grid is through reactive power control. When we integrate these two together, the benefits are much greater in integrated volt-VAR control. Spending a lot of time looking at renewables like we talked about, that's new. We're adding more and more sensors to the grid. And the reason is, you know, in many places we have very much of an aging infrastructure, right? For instance, in the United States, the average age of a transformer today is over 42 years old, right? And I know in the UK it's over 38 years old. Transformers are multi-million-dollar assets. We can't afford to replace all of them at the same time. How do we extend the life of an asset that is aging? Well, we can, for a small amount of money, we can invest in microprocessor-based devices like this. And for instance, here we can take the oil from the main tank of the transformer, send it through this device, and this device can detect up to nine different gases that are dissolved in the oil. And the presence of any one of those gases is a failure mode that's occurring in the transformer. Okay? So we can know the health of that asset on a continuous basis. And instead of taking a chance and not monitoring a $2 million or $3 million asset for a small investment, we can add it to the transformer and we know the health, called transformer monitoring and diagnostics on a continuous basis. And in fact, that's the second strongest business case today of any smart grid solution. I think that, you know, the one area of emphasis is with smart grid is the predominant spending in smart grid has moved from smart metering. Remember at the beginning of smart grid 6 years ago or so, almost every project was a smart metering project. And the bad part about that was when I would say something about smart grid to somebody, they would say, "Oh, you mean smart metering?" And I said, "No, smart grid is much more than just smart metering." But all the projects in the beginning were all smart metering, and people thought that's what smart grid was. And smart grid, we say a GE smart grid goes from turbine to toaster, right? Turbine to toaster. So it's not just metering, but it's generation, transmission, distribution, customer, where the toaster, right, is in the customer's home. That's a wide landscape, much, much more than just metering. So we're focused now, a lot of us, on the distribution system, a separate SCADA system, a separate control system for distribution management, logic in the distribution substation. Like we said, in the US, half of the distribution substations aren't automated. And then logic downstream of the substation on the feeders. This is the strongest business case today of any smart grid technology, is right here. And then smart metering. And I want to show you that there's a lot more information we get from smart meters than just the metering information itself. Okay? So let's look at the concept of a solution. And we spent a lot of time, this is six years ago or so, and the main thing with a solution is we spend more time with the customer up front, the utility, in terms of their business needs. And after gathering information, we said, what are the solutions that have the strongest business cases for electric utilities? And first was asset optimization. And the first asset we're focused on is key transformers, transformer monitoring and diagnostics. Second is demand response and demand optimization. Third is smart metering with two-way communications. Then optimizing the distribution system, optimizing the transmission system, looking at synchrophasers, and really utilizing the phaser measurement unit information much better. And then lastly is workforce and engineering design optimization. Workforce is extremely important. You know, I said we have an aging infrastructure. We also have an aging workforce, right? And in the United States, an example, there was a report issued about a year and a half ago by PricewaterhouseCoopers, and it's with a lot of detailed information, but the bottom line was, in our industry, in the United States, within the next 5 years, 40% of the engineers today and 60% of the executives today will retire. Okay? 40% of the engineers today and 60% of the executives will retire in the next 5 years. Which, you know, for young professionals, it's an ideal situation, right? There's tremendous demand and not enough supply, okay? But we need to focus on the workforce. How can we capture that experience? How can we add tools and you know, more specific information to the workforce so the workforce can be more efficient, right? How much more automation can we do? So I want to show you the technology roadmap here of the 6 solutions, color-coded. And let's just take a look at distribution optimization. Let's look at the light blue boxes here. So remember, in the beginning I said standards are important, extremely important. Interoperability is key. So think of all those light blue boxes before we go over them from different vendors. How can we successfully have them communicate with each other and exchange information with each other, right? All from different companies, okay? This is not easy. These are software applications. So there's fault detection, isolation, restoration, integrated volvar control, optimal feeder reconfiguration, distribution power analysis. That's our 3-phase unbalanced load flow here. These are the systems, distribution management, outage management, and these are located in the office or the control center, all right? Now we go down to the substation, and here we have our data concentrator, our station controller. And like I said, we're distributing the intelligence so we can run volvar control and fault detection, isolation, restoration at the substation level. Have a local user interface and other microprocessor-based devices in the substation. Now we go outside the substation, and on the feeder, distribution feeders, we have switches and breakers. We have sectionalizing devices. We need these to support fault detection, isolation, restoration. When we detect a fault and we locate it, when we want to isolate it, right, we need switches or sectionalizing devices on each side of that fault so we can open them up and isolate the fault. Then we need volt-var devices, capacitor banks, voltage regulators to support integrated volvar control. So this is the logic, and then this is the equipment out in the field and the smart controllers and the two-way communications. So think of, it's not trivial to have all these light blue boxes from different vendors be able to interoperate, okay? So how can we make the grid more resilient? Well, first off, we need to invest in 5 key components. Smart meters, metering communications, which we call automated metering infrastructure, and 3 systems: the geographic information system, outage management system, and distribution management system, right? But it's not the value of those separately, but it's the integration of those which makes the grid more resilient. For instance, I need from the meters, not just the meter readings, but I need the voltage from certain meters at the ends of certain feeders to put in a network model in the distribution management system. When I do volt-var control, I need to know the voltage at the end of the feeder. I don't know what it is in Mexico, but in the United States we have an American National Standard, ANSI standard, that says the voltage at the customers, the voltage delivered, the voltage at the customer site must be 120 plus or minus 5%. So it must be between 114 volts and 126 volts by law, okay? So I need to know what is the voltage near the end of a feeder, a long feeder with a lot of voltage drop. And I can use smart meters, certain smart meters for that. The other thing is, and this is really important for an outage, is every smart meter has enough energy in it once voltage is lost to have one last gasp communication, right? So there's enough energy in a meter, right, that when there's an outage, there's enough energy for one final communication upstream to the utility, and we send that information to the outage management system. We don't need phone calls from customers. Our smart meters will tell us every single customer that's without electricity and the time it occurred automatically, okay? Very key, because utility, before they can start restoration, what's the first step? Is assessing the extent of the damage, right? How many customers are without electricity? Where are they located, right? And this helps tremendously. The geographic information system is your reference system for the network model, for outage management and distribution management, right? This is key. That's your reference system. Must be kept up to date as construction changes are made in the field. We keep the GIS up to date. Another key link is the distribution management system with the outage management. You know, a SCADA system, when a status change occurs, like a breaker trips, we know about it in SCADA typically within 2 seconds, right? So let's say a distribution feeder breaker trips. We send that status change to the outage management system. Here we have the network model. So once the OMS knows that a feeder is de-energized, it knows exactly which customers are fed from that feeder. So it knows, okay, all these customers are now have an outage and the time it occurred from one status change, right? And then customers, typically we rely on phone calls to the utility that they're without power. But as we said, social media, using that to a much greater extent. Take the human out of the loop, say use Twitter and get tweet information from customers and bring that right in to the outage management system. We showed that that could be done a couple of years ago with technology, and that's what I wrote about in the article 2.5 years ago. Okay? So, one of the big trends today is the impact of the Internet of Things. A year ago, a new consortium was formed called the Industrial Internet Consortium. GE, AT&T, Cisco, IBM are all founding members of this new consortium. And it's looking at the Internet of Things and the next productivity revolution by connecting intelligent machines with people at work, okay? And so you can Google, you know, Industrial Internet Consortium and find out all the work that's going on. There's a number of test beds that are in operation now. But the concept is we connect intelligent machines, the technology and communication to cost effectively connect machines with the power of big data, big analytics, and industry physics, and then connecting with people at work. Connecting people, no matter where you are, any way we can connect, and any time for intelligent operation, okay? So you're going to see a lot more of this with development of new technology and the impact. And I still say that we've always had a lot of data, but we can be more creative with how we analyze that data, you know, with analytics. To me, analytics is something in the future here that we should spend more time on, because there's new value propositions we can provide with analyzing data in different ways. And just 5 different ways that we're looking at this at GE is more insight into metering, more insight into outage with dashboards and predictive outage analytics, more insight into reliability with predictive vegetation management, asset health analysis, and system health analysis, and looking at life cycle analysis and portfolio optimization. Renewables insight, with both PV and wind and electric vehicles. And then lastly is the customer, right? So with smart grids 6 years ago, 7 years ago, one of the lessons we learned right away was, wow, the customer is a new stakeholder in smart grid. The customer was not a stakeholder in what we did before. My whole career was on the grid side, has been on the grid side, upstream of the meter, right? You know, monitoring, control, analysis. Now all of a sudden we got the customer as a new stakeholder. How do we engage the customer, right? Not all customers are the same. When we do demand response, smart metering, we have to know that we have to segment customers. There's 5 or 6 different types of customers with different characteristics and different price points. So customer insight is social media integration, customer segmentation, customer engagement. If you're going to do anything on the customer side of smart grid, it's a whole different world, okay? And we started a new organization 5.5 years ago called the Smart Grid Consumer Collaborative. It's about 120 organizations, and we pool our dues money, and we do research on the customer side of smart grid only. And every year we issue in January at the Distributech conference, a State of the Consumer report. And this past January was 7 key themes based on the research we did last year. That if you were doing any kind of a project on the customer side of smart grid, you need to take into account these 7 key themes, okay? It's called the State of the Consumer report. So this is something that's new for us, but we need to pay much more attention to, okay? And then enterprise data management. Typically we have a lot of systems, we have a lot of microprocessor-based devices and existing databases and repositories, but they're not really connected, okay? In fact, each of the groups in the utility, each of the groups in the organization has their own devices, has their own systems and their own databases, and we really work in a siloed way, right? Where each group has their own data, their own applications, and really don't work across silos. To get the benefits, we need to work holistically across the organization and bring together these 3, okay? And this is an IT infrastructure that does that, okay? And this is a topic we could spend a lot more time on, but I've done a number of projects with utilities, and the benefits are great by doing this the right way. You can realize many more benefits of your investment in systems and microprocessor-based devices. So, with respect to standards, in 2010, we knew smart grid was a wide landscape, right? Turbine to toaster. We said we need to get a good handle on what smart grid looks like. So let's take one sheet of paper and a pencil, and let's draw all of smart grid on that one sheet of paper. What would that look like? And this is what we call the Smart Grid Conceptual Reference Model, which is 7 domains interconnected this way. And this is a high-level conceptual model of smart grid. This is an industry standard. We work closely with the European standards folks. They have another domain here that they've added. So we harmonize architectures across countries, okay? But if we look at all, there's a lot of standards out there. IEEE has identified 100 standards. IEC has identified about 100 standards that touch on smart grid. But what I did was looked at what are the most important standards, what are the foundational or fundamental standards for smart grid, and it's these 16. You don't have to think about all these other standards. If you really want to focus on the most important, so if you're doing a research at the university or a project at a utility or developing a product at GE, I've got to have at least one or more of these standards included, or I will not be successful. I will not interoperate successfully, okay? Guaranteed. So these are the critical standards here that span generation, transmission, distribution, and customer. And so there's a group we call the Smart Grid Interoperability Panel that coordinates all the smart grid standards work in North America, but we harmonize across the world. And as technology changes, say what gaps do we have, and then we fill those gaps with new standards, and that's what each of these light green boxes are, is a gap that was identified and a new standard being developed. Okay, so this is a group that anyone can participate in. There's over 220 organizations around the world all working together. And what's nice is this work has a lot of benefits, because today, if we want to buy a new control center and we want to exchange information with another control center, across the world there's one way of doing it. We've standardized across the world on one way of doing it, which is an IEC standard, where we also call it Inter-Control Center Communications Protocol. So no matter where you are in the world, if you're going to buy a new DMS or EMS, some kind of a SCADA system, you'll have at least one ICCP communications port. And even within a utility, we use ICCP for the EMS to communicate with the DMS. Okay? One standard. From control center to field equipment, there's really two standards. If it's North America, use DNP3, which is IEEE 1815. If it's a European supplier, they use what we call IEC 870-5, 101 for serial communications and 104 for network. And in the field, it's typically IEC 61850, which is the worldwide standard, substation automation, communications, and protection, and DNP3. So it's really nice. You know, it wasn't long ago that we had a number of different choices. This is much easier now because we've standardized and converged on a lot less choices. This is the website for all the standards work, sgip.org. Welcome you to look at that. Also, the website for the consumer work, the Smart Grid Consumer Collaborative, is smartgridcc.org. Okay? Now, new policies are needed, a new regulatory model. We have aging infrastructure, we have greater sensitivity to grid disturbances, and we talked about the increasing complexity of distribution networks. The existing regulatory models don't work well with the changes that we're undergoing. So we wrote a white paper a couple years ago called Incentive-Based Regulation, which is a public document. We actually wrote it in together with a former state regulator for the state of Ohio, who has a lot of experience with regulatory policy. And what it does is it ties utility profits to performance and the end-use customer benefits in the investment that the utility makes. And what we want to do is look at reliability, efficiency, power factor, customer satisfaction, safety, and other output-based metrics. That's what we want the model to emphasize. And some good examples here, two in the United States, the state of Illinois with Commonwealth Edison, state of Maryland with Baltimore Gas and Electric, and the United Kingdom. Okay, these are very good models, new models of implementing incentive-based regulation. All right?
I was asking, in your experience, what is the main problems that you see in the implementation of smart grids in the U.S. and other countries? You mentioned about there are some policy, regulatory problems, perhaps, or aspects, and technology maybe other. So I would appreciate if you can comment on that.
Yeah. So excellent question. You know, what are our experiences around the world? And, you know, we've implemented a lot of smart grid technology, right? And we've implemented it because many countries have had stimulus programs. Right? In the United States, we had $4.5 billion for electric utilities to buy and implement smart grid projects. But most countries in the world had similar stimulus programs. Well, one thing that we did, after 18 months of deploying smart grid technology, we stopped and we looked backwards. And we said, what were our initial assumptions? And what have we learned? And what changes do we need to make going forward? Okay? And I actually have 4 PowerPoint slides that summarize the lessons we learned. But I wrote a smart grid newsletter. So if you go to the IEEE Smart Grid portal, July of 2011, I wrote this. But some of the lessons we learned, just briefly. One is the importance of, one was that on the integrated solutions, when we began to deploy integrated solutions, we found that not all the technology components were as mature as advertised. Right? And you know, they say a chain is as strong as its weakest link. Right? So an integrated solution, one component that's not working properly affects the whole solution. So we had to do a lot of field upgrading and field replacement, okay, that we didn't anticipate, okay? Second was the importance of standards. You know, we had technology components from different vendors. We go out in the field and devices don't talk to each other. They don't exchange information with each other, okay? Both vendors said, well, we've implemented DNP3 standard, but that doesn't mean that they're going to interoperate. There's 2 parts. One is compliance to the standard, but the second, more important part is tested for interoperability. Okay? Compliance doesn't guarantee interoperability. That's an important point. Third lesson we learned was testing. The value of we thought we tested adequately in the factory. Then we went out in the field. The thing we forgot to do was, remember, these integrated solutions can go from substation to the control center or the office. We didn't do enough end-to-end testing. End-to-end. You can test the meter and the communications from the meter, and it works fine. You go out in the field, now the meter is communicating to the head-end system. We call the network management system that manages the metering communications, and it wouldn't work. We didn't test that in the factory. End-to-end testing, okay? Another one was when you have these solutions and you have technology coming from all different vendors being shipped to the utility, it's a real management challenge to manage the shipments of hardware and software and all these different pieces from different vendors. Okay, that has to be planned in advance. But more importantly to me, each of the smart grid projects have a project manager, right? We can have the best technology in the world that's standards-based, but if we don't have a very experienced, good project manager, that project can be a failure with the best technology. Project management, a lesson we learned, project management is key to success, okay? And then in addition to that, all the project managers report up to a program management office. We need to make sure that PMO has consistent reporting guidelines, escalation policies. You need consistent project management across the whole organization. Don't let each project manager manage the way they want to, okay? And I guess bottom line was, we said in the utility, spend time and put together what we said your A team, your very best technical people and project management people, because there's going to be challenges in the field that need to be resolved, and you need your best technical people for that, but you also need your best project management people to manage the project. And then the last lesson we learned was how important the customer was. The customer is a new stakeholder. We never engaged the customer before. We didn't understand the customer. You can't go out and put smart meters on homes without talking to the customer first. Look what happened to Pacific Gas and Electric in California. Look what happened in Texas when that happened, okay? You can't do that. You've got to spend time with the customer, engage the customer, make sure the customer understands the new technology and what you're doing before you do anything with installation. Those are some of the, but I wrote a newsletter on that, and I can send you a link to the newsletter if you'd like to.
I'm Dante Franco from IG Transformers. Can you talk about the impact of the electric vehicles in the smart grids? So, for example, you can use even the batteries of the car for going power into the system. Is there any analysis about it?
Yeah, so with electric vehicles, there's a couple of things with electric vehicles. One would be to make sure we add intelligence into the grid, because what we don't want is we don't want everyone coming home at 5 o'clock or 6 o'clock plugging in their electric vehicle and having a charge right away, because we're in the middle of an evening peak already, and that would just make the peak worse. So we need intelligence in the grid to say, okay, it's plugged in, but let's delay the charging until 11 o'clock at night, overnight. Why? Because we did analysis in the United States with the Department of Energy. Without building any new power plants in the United States, we have enough generation capacity that's reduced overnight, right? We have enough generation capacity today without building any new power plants. We can charge 10 million electric vehicles overnight with the present generation capacity. So the first thing is intelligence to the grid. Second thing is there's been some projects where take a number of electric vehicles, and we call V2G, vehicle to grid, where you take the stored energy from the batteries in the vehicles and move it towards the grid, right, to supply the grid. There's been some projects in California with Google and a parking garage that Google has, and Pacific Gas and Electric, and projects at PJM. PJM is the regional transmission operator, Pennsylvania, Jersey, Maryland, right? PJM is I would say, the most progressive RTO, regional transmission operator, and you can look at the projects that they've done. These have been pilot projects, and they've shown that it would work, so that's as far as it's gone to this point. A couple pilot projects prove the concept, but there's nothing broader scale than that yet. I think there's a lot of issues that need to be addressed. If I park my electric vehicle and I have a doctor's appointment at noon, I want to make sure I have enough charge in my car to go to the doctor. And if the utility's pulling that energy out of my battery to supply the grid, there's this, and the charge-discharge cycles. So if V2G is using my car every day to supply the grid, that wear and tear on my battery reduces the lifetime of my battery. It adds additional charge-discharge cycles. So these are things that have to be taken into account with a V2G program. But you can Google PG&E and Google and find out their project and the PJM project. There's published results. Okay.
Thank you very much for your talk. Alberto Reyes, aquí del Instituto de Investigaciones Eléctricas. Well, you mentioned something about the solution to this new smarter grid. Some of them was related to optimization, right? I understand, right? I understand well how to implement optimization when to the demand or the dispatch optimization. Yeah, but what I don't understand well is how to implement the workforce optimization. Do you have any comment about that?
Yeah, that's what's been happening with the workforce now is looking at ways that we can provide more information, more timely information, and more detailed information to the field force, out in the trucks, because many times they may not have the right piece of equipment with them because they didn't have the right data, or they may be going to the wrong site. There's confusion. So there's like we have something called field force automation. It's a combination of mobile data, right, communications out to the trucks. So looking at, for instance, the digitized maps from the geographic information system and sending some of that mapping information out to the field force, so you have more detailed information, so you can be more efficient and more productive, and possibly less people, less time, and be able to do more work orders in a day. So it's a whole list of things that it's bundled under what we call field force automation, and it's been proven with a lot of different utilities in terms of increasing the efficiency and the productivity of the field force. Okay.
Hola, Salvador González del Instituto de Investigaciones Eléctricas. John, it has been a very clarifying talk. I appreciate it very much. But it also reflects that there are very many things to be done to get into the, let's say, grid of the future, or smart grid. In your opinion, I mean, it can be cumbersome, a very huge task for a utility to decide where and when to invest in different aspects.
Right.
In your opinion, what would be the order of the steps recommended for a utility so that their investment will get a return in less time and in a more favorable situation?
Yeah. I mean, when I showed the slide of 6 different solutions as an example, it's never the case where you talk to a utility and you try to do all 6 at the same time. Okay, I would say think of that as more of you go into a restaurant and there's a buffet. And you have a lot of different choices of what to eat in the buffet. But you will choose one particular food item that's your favorite first, and you'll just take that one and take it to the table and eat. I'll go and I'll take a different one, and I'll come back to the table and eat. So so when I talk to a utility and I say these are the possible solutions, I have to be flexible and say, for you, this one solution has the strongest business case for you. Let's focus on that first, okay? I go to another utility and say, it's different, for you, this solution has a stronger business case than the others. Let's focus on that. So think of what we talked about as more of a total menu of selections, but you're right. No one can do all of those or even half of those at the same time. It's too much. You don't want to do that. You don't have the resources or the budget to do it. So together we figure out with each utility what should we focus on first. But I think what's most important in this is, and not a lot of utilities do this, okay? Before I spend any money at all, I want to have a holistic, organization-wide strategy or roadmap for smart grid. I want to bring together every group in the organization, and let's think about, there's all these solutions available. What makes sense for us, for our utility? What should we do first? What should we do second? What should we do third? And let's map it out over 10 or 15 years. Let's have a long-term plan. In California, the best thing that happened in California, the California Public Utility Commission required by law the three large utilities, Pacific Gas and Electric, Southern California Edison, and San Diego Gas and Electric, they had to put a holistic strategy together for smart grid by law and submit it to the California Public Utility Commission by a certain date, like 3 years ago. And it forced each of them to come together holistically, break down the silos, the walls of each group, and all the groups work together. Then you know, as an organization, when you look at the solutions, you have your game plan. You know what you're going to focus on. You know what resources you have available. You know what budget money you have available, and you have a long-term plan. If you don't do that, and this happens with many utilities, this group gets an idea for a project. They have a little bit of budget money. They buy equipment and they put it in. Okay. This group has another idea for a project. They get some budget money and they put it in. What happens? In a short period of time, you've got lots of different projects going on, but there's no alignment with any strategy organization-wide. What happens is you end up with a lot of stranded investment, stranded assets. Money is spent. When a project's done, there's no second step because there was no long-term plan. You know, everything just ends, you know? And so the thing to do is long-term strategy and then focus on, you know, one or two things at a time and do those well. And it's very easy to, with any utility, to say, there's no question this solution has the strongest business case for you. You know, let's focus on that. So it's easy to do, but it requires really the CEO and the leadership of the utility to say, hey, we aren't going to be doing 20 different projects group by group. Let's get together as an organization first, have a strategy as an organization. Then what we do will be aligned with our overall strategy. Okay. Any other questions or comments?
Thank you very much for your talk. My name is Rito Mijares from here for the Institute. All the electric elements in the grid are aging, and I mean transmission lines, transformers, and replace all of them. It is expensive. What we have done is retrofit them with certain intelligence. We have used controllers, information technology. We have the joy of bidirectional energy and communications. And what we've been doing is retrofitting them, it's in general, to make them smart. But I think that the tendency would be to make, for instance, a transformer smart from the fabric. You know, they could be manufactured smart with sensors embedded on it.
Right.
The question is, what is the tendency that we could have smart electric elements in the grid of if we ever would have them, because it is expensive?
No, to me, that's what we should be doing. You know, is we can't replace everything at the same time. So the other thing is, if we don't have sensors, we don't know what's happening. And if we don't know what's happening, we tend to leave what we call a margin or a buffer in the decisions we make, because we have to allow for the risk, right? So to me, we should move to dynamic ratings, right? The ratings, all the equipment on the grid should be based on actual conditions, and we know the actual conditions based on sensors. Now, one of the challenges with distribution, you know, we can put a DMS at the utility with all these fancy application programs, but you can only optimize what you know is happening in the field. When you have a lot of substations with no automation, you have no data coming back. You're blind, and the feeders are even worse. We have what we call intelligent line monitoring, sensors you add on the distribution feeders. So I think what's going to happen with the emphasis on distribution, the emphasis on DMS, it requires us now to do more with putting sensors in the substations and feeders, because our DMS, it can't do anything unless it first step is have real-time information, telemetry coming back.
But we are retrofitting it. I mean, the sensor is there, and we are adding them on.
Yeah.
In the future, these elements could be with the sensors embedded in there. If we could have them.
Yeah.
It is expensive, I know. And it has been actually a lot of opportunities for us engineers trying to introduce these sensors, elements, communications, and stuff.
In fact, I see that, to me, that's a research area in terms of every piece of equipment that we use today should have embedded sensors in it, every piece. And if we don't do it today, what do we need to do in the future to? I agree with it. Transformers today, typically now, when a utility buys a transformer, the standard specification for buying typically today requires a transformer monitoring and diagnostic unit to be bought with the transformer. So when a transformer is being built, those sensors are put inside the transformer at the time of manufacture. But every piece of equipment should have some kind of monitoring. And then from a system point of view, the term is we can actually operate the system closer to the ratings. We can get more use of the infrastructure that we paid for because we have real-time information, and our ratings are based on real-time ratings. And so I see that, but there's a lot of technology that needs to be developed, because today you're right, we have a lot of equipment that we don't have sensors in the equipment. It's a really good field going forward. I see it it's an opportunity, and really the goal should be that every piece of equipment has information coming back, and then we can optimize the operation on a real-time basis. Yeah.
Me da mucho gusto entregarle a nuestro conferenciante. It is my pleasure to award you on behalf of the Instituto de Investigaciones Eléctricas this certificate of appreciation to Dr. John McDonald in recognition for sharing his expertise with the conference The Future of Energy, Smart Grid and Beyond in the occasion of celebrating our first 40th anniversary. John, thank you very much.
Thank you.